Fundamental Theorem of Calculus, Part 2. If f is a continuous function on an interval I and contains any point called a, then for every x in I, the derivative with respect to x of the definite integral from a to x of the function f of t dt equals f of x. What is this telling us? This is saying that the derivative of the antiderivative, remember these are inverse processes, so they undo each other, leaves us with just the function f. Now notice how inside the function was t, but we have x plugged into the function instead. Well, how does that work? Imagine that we did, for example, the derivative with respect to x of the integral from 5 to x of the function cosine of t dt. So we're doing the derivative of this integral. Let's imagine that we want to do this the long way. So what does that mean? First, we work from the inside. So we take the antiderivative of cosine of t, that is sine of t, and we evaluate sine of t from 5 to x. So again, we're doing this part first. So that requires plugging in x, so sine of x, and plugging in 5 and subtracting those values. Now, next is taking the derivative with respect to x. Derivative with respect to x of sine of x is cosine of x, and derivative of this constant is 0. So we're left with just cosine of x. Notice that if we had thought about the fact that the derivative and the antiderivative are just inverses of each other, we could simply have gone straight to saying the answer is that leftover integrand with that x plugged in where the t was. So let's remember that derivative and antiderivative are inverse processes and use this shortcut. In number 1, it says evaluate the derivative with respect to x of the integral from 2 to x of the square root of 1 plus t squared dt. So remembering that derivative and antiderivative are inverse processes, I see the variable is x, that goes in place of the t, and my answer is square root of 1 plus x squared. Done. So we just remember that these are inverse processes. Number 2, for f of x equals integral from 5 to x of 1 over 3t squared dt, find f of 5. This means I plug the 5 in where the x was. So here's the x. This will be the integral from 5 to 5 of 1 over 3t squared dt. Notice that I'm doing a definite integral with the limits the same, therefore the net area is 0. Part B says do f prime of x. If this is f of x, f prime of x means take the derivative with respect to x of this f of x function, the integral from 5 to x of 1 over 3t squared dt. Remembering that derivative and antiderivative are inverse processes, I plug the new variable in where the old variable was. 1 over 3x squared is my answer. You may be asking, where does the dt go in all of this? Well, remember that the dt is attached to the integral symbol. So if the integral goes away, the dt goes away as well. Part C, f prime of 2. So remember that we just did f prime of x, and we got 1 over 3x squared. Now, if we want f prime of 2, we're plugging the 2 in. We could leave it like that or clean it up a bit. Number 3, find f prime of x if f of x equals the integral from negative pi over 3 to x cubed of cosine of t dt. So again, this is saying find the derivative f prime means the derivative of what f of x was, which was an antiderivative, negative pi over 2 to x cubed of cosine of t dt. Now you might notice that this time the upper limit is x cubed instead of just x. Let's take a peek back at this example we did at the beginning, where it was a little bit simpler and the upper limit was just x. If the upper limit, instead of just x, were x cubed, and in the long process of doing this, I were to be plugging in x cubed instead of just x, when I do the derivative, I have a composite function. So I'm not just doing the derivative of the outside, sine to cosine, but then I have to multiply by the derivative of the inside to make 3x squared cosine of x cubed. So when you see that there's more than just x, you should think, let's do the chain rule. Because we're plugging in more than just x. We're plugging in another function. It creates a composite function. So we might actually write this in such a way that it applies to all definite integrals, not just if we're going from a constant to x, but if these are any functions of x. So let's show a more spruced up version of this fundamental theorem of calculus part 2. So that will look more like this. The derivative with respect to x of the integral that goes from g of x to h of x of f of t dt will equal, now of course, the derivative still cancels out the antiderivative. That part doesn't change. Let's remember our first fundamental theorem of calculus, or fundamental theorem of calculus part 1, which says the integral from a to b of f of x dx is antiderivative evaluated at b minus antiderivative evaluated at a, or capital F of b minus capital F of a. So we apply that here, and we are doing the derivative of the antiderivative. So this f doesn't change to capital F. It stays as lowercase f, but we're plugging in h of x, the upper limit. But since this is a derivative, I have to apply the chain rule. So the chain rule says multiply by the derivative of the inner function h prime of x, and then minus f with g of x plugged in, the lower limit, and then because I'm plugging in more than just x, times the derivative of what I plugged in, g prime of x. Now this will apply to all possible examples. Like in number 1, if we were to do this the way of applying the fundamental theorem of calculus part 1 and the chain rule, this would say, okay, cancels out, I'm left with square root of 1 plus x squared times the derivative of what I plugged in, 1, minus square root of, now I plug 2 in, 1 plus 2 squared times the derivative of what I plugged in, which is 0. But notice, because this is 0, this makes 0, and because I'm multiplying by 1, in the end, that just equals square root of 1 plus x squared. So I still get just square root of 1 plus x squared. So if I remember I have a constant at the bottom, I'm not really going to have to worry about that chain rule. Back to number 3, here we do have to worry about this chain rule. So let's go ahead and apply it. Derivative of antiderivative, inverse processes. Leaves me with just cosine of t, but I'm plugging in the x cubed where the t was. So cosine of x cubed, and then times the derivative of what I plugged in, 3x squared, minus cosine of lower limit, negative pi over 2, but times the derivative of that. That's a constant, so that's times 0. Remember, multiplying by 0 That's gone, so I'm left with just 3x squared times cosine of x cubed. So we remember to apply the chain rule when we're plugging in more than just x. Number 4, find f prime of x if f of x equals the integral from x plus 1 to 2x cubed of t minus 5 dt. So let's start by saying f prime of x means I'm saying the derivative with respect to x of the integral from x plus 1 to 2x cubed of the quantity t minus 5 dt. And then I remember derivative and antiderivative are inverse processes, so those cancel each other out. Let's apply the Fundamental Theorem of Calculus Part 1 with the part I have left over. So remember, instead of writing t, I'm going to be plugging in the upper limit first. So 2x cubed in place of the t minus 5. Then I multiply by the derivative of what I plugged in, applying the chain rule, 6x squared. Minus, now the lower limit gets plugged in, so x plus 1 minus 5, and applying the chain rule, the derivative of x plus 1 is 1. So just a little reminder that this part right here and this part right here, I'm applying the chain rule. Now we can clean it up a bit, even though we do have this derivative. Taking away some parentheses, combining like terms, and then distributing 12x to the 5th minus 30x squared minus x plus 4 gives me a slightly cleaner answer. Thanks for watching.